4 pi r. Or IL somewhere. Maybe you can put the IL on. And actually you can say R is just equal to R. Okay, you can simplify it. And that should be the expression for the magnetic field. So with these expressions, we can write down the field in terms of spherical waves. But then we know how to represent the spherical wave with plane waves right now, using the Sommerfeld identity. And we actually have a few Sommerfeld identities to play with. Which one should we take? We can use the Weyl identity, which is a double integral. We can use the Sommerfeld identity, which has only a single integral. So from a numerical viewpoint, it's better to use the Sommerfeld identity, because we only have to grapple with a single integral. So we look at the vertical electric dipole case. And let's call this the VED. And then we say that alpha then is pointing in a z hat direction. And you have a vertical electric dipole. It would be nice to visualize in your mind as to how the electromagnetic field looks like. The electric field will look something like this, right? In the near field, it looks something like this. This is like a quasi-static field that I'm sketching. Of course, in the far field, we start to have lobes and then we start to fly away. Okay, the static field is pretty much stuck to the source. How would the magnetic field look like? Remember how the magnetic field of an electric dipole that is vertically oriented, how does it look like? Very good, it goes around in a circle. Okay, so the magnetic field would go around in this manner. This is E. And actually, phi is entirely oriented in the H is entirely oriented in the phi direction. Okay? So we know that this kind of field must be Tm or Te. If I were to label it, even before I start with my math, Tm, right? So it must be a kind of Tm field. And so if it's a Tm field, what components of the electromagnetic field should I use to characterize this field? No. Ez. Okay, Tm means Ez, Te means Hz. This is only one scalar component, not 3 or not 2, but you have suggested use the simplest one, which is in this case Ez. Okay, so let's try to look at this thing and extract the Ez component of this thing. And this is an I, so if I were to extract a Z, if this is pointing in a Z hat direction, I dot Z hat just give me Z. Okay, the first term will just give me Z hat. Okay. And then if I only am interested in the Z component of this electric field, I will only take the partial Z of this. But this, since this is Z hat, this gives me another partial Z from there. And then I have to put the K naught somewhere. Maybe I can put the K naught square somewhere here. And then e to the I K0 R over 4 pi R. Okay? And I have to put the IL somewhere. Let me put the IL here. And this is no good because it cannot propagate the spherical wave through a late medium. So let me replace this with the Sommerfeld identity and get the fact that this is equal to I omega mu. Let me use mu naught to indicate that this is the free phase part. Okay? And then, actually I don't have to put a Z hat there. Since I put the Z hat there, I must have put one on the left hand side. I can now remove the Z hat. Then I would have 1 over K naught square. I can take it out. So it would be K naught square plus partial square partial Z square. And then now I replace what I have there by the Sommerfeld identity, which is, let me try to recall what it is, right? It's 0 to infinity, the k rho e to the I k, k rho over kz, j0, k rho, e to the I kz, z. And then just replacing that with the Sommerfeld identity. What?
Is it 0 to infinity or minus infinity to infinity?
Since I use J0, so I use 0. Okay? There should be an I somewhere, then I should be put here. I can replace that with a minus sign. Okay? So this is the expansion of this field. This would be a Tm field because I'm only looking at an EZ component. And this can be reverted back to plane wave using some the Will identity. But let's not do that. Let's just write this in a concise form, so there's always a single integral. But you know the physical meaning of this. This is a Bessel function is the sum of plane wave propagating in all direction plus a plane wave propagating in the z direction. And this wave is easy to propagate through a layered medium. Okay, so we can subsequently add layered medium. It would be a piece of cake just to solve this problem. Okay, maybe not a piece of cake for all of us, but maybe a piece of cake, right? It's an American idiom. It means it's easy as eating a piece of cake. Okay. So now if I were to bring this inside, I bring this operator inside, and it can just operate on this. You can just operate on that. What would partial square partial z squared do when it operates on that function over there?
Kz squared.
Yes?
Kz squared.
Kz squared, right? Does it only produce a kz squared? What?
I squared kz squared.
I squared kz squared. Okay, you're partially correct. To get 100% mark, what else must you add?
Absolute. We have to count the absolute value part.
The absolute value part actually complicates the situation. If you differentiate it one time, the absolute part will give you a plus or minus sign, right? You differentiate it two times, give you a delta function. So that will give you the complication. But let's just assume that z is larger than 0 to make things simpler. Okay, when z is larger than 0, then we don't have to worry about the delta function term that's produced. So giving you kz squared or minus kz squared is only partially correct. You get 95% of the mark.
Itself.
Yes?
But then it has itself.
Times itself, yes. But there's what I want to emphasize is that there's actually a direct delta function term generated in this process. And I hate to carry the direct delta function term around. It's too complicated. Let's just assume that z is larger than 0. So for z larger than 0, I can actually rewrite this equation. Actually, you can also simplify this thing and write this as minus kz squared. This is k naught squared minus kz squared, right? If I take it inside, what is k naught squared minus kz squared? K rho squared. So I can actually consolidate everything and write this as k rho cubed. I had a k rho squared coming from there over kz. K0 rho e to the I k z z. Okay. But I have to add a condition that this statement is only true if I'm not at a z equals 0 point. At z equals 0 point, I have to carry this direct delta function around. But let's not quibble over that direct delta function. We know they're somewhere around, but not worrying about it. So this is the dipole field, expanded in terms of a plane wave now. Let's show that there's no, let's show that hz is equal to 0. Because if it's truly a Tm field, then this has to be true. And let's look at the second expression. if alpha had been pointing in the z hat direction, what is curl of z hat? You will never have a z component, right? So hz must be 0. So clearly indicating that this is a Tm field. So hx and hy are non-zero, but hz is equal to 0. Okay? So this is the vertical electric dipole field. And you can, okay, give me 5 more minutes. Then we take a break. You can show also using the other identity that this Ez can also be written as minus IL. You can simplify this over 8 pi omega epsilon naught. Okay, this is omega square mu epsilon. So the mu cancel, leaving that behind. And then using the other identity, or you unfold this integration and replacing this with that, there's a 2 that contributes to this 8. 4 times 2 equals 8. K rho e to the I k z z. And again, this is only valid for z larger than 0. This identity is preferred because you can do contour deformation with it quite easily. Okay? You do contour deformation with it quite easily. And then comes the important part. What happens now if I were to add the electric dipole on top of a layered medium? What happens if I add this dipole on top of the layered medium? How can I write down, say, the field in region 0? So I call it region 0. Maybe I call it region 1. I call it region 1. Okay. So how would I write down the solution in region 1, say? Using my physical intuition first, and then check for mathematical correctness after that. If I use my physical insight first, if I were to write down the solution in region 1, the solution in region 1 can be expanded using this expression, and then it will be interpreted as a source producing plane waves in all directions. They're not truly plane waves, they're actually Bessel wave and anchor wave, but you know that those can be expanded back into plane waves. So my physical intuition is to see this picture. Okay, so if I were to write down the field in region 1, it will consist of, first, the term as if the layered medium is not there. So it sees a region 1 electromagnetic property. Okay, and then I will call this K1Z. K1Z I define to be the wave number of region 1 minus K rho squared. And then I will write the rest down. K rho e to the I K1Z Z. Okay. This is the solution in region 1, assuming that the layered medium is not there. What would the presence of the layered medium do to this solution, according to your physical intuition?
Sum and reflected.
Sum, right? You just have to add a reflected wave. The reflected wave will propagate in the positive z direction, and that when z equals minus d1, okay, this phase will come up to be correct, and then you add a generalized reflection coefficient for Tm waves, Tm plane wave. Okay, this generalized reflection coefficient would have to be according to the kind of plane wave that are incident on it, okay, it would be a generalized reflection coefficient depending on k rho, function of k rho. Okay, so you can think of this as a function of k rho. That is the only thing you have to do. This is the physical intuition that motivates you to write down the solution. I just think of everything as plane waves, and then just write the solution down by inspection. And is this really correct? You have to ask yourself, is this mathematically correct? And then you start to invoke those things like completeness axiom, and the fact that these functions are complete, that's why it allows you to do things like that. And it almost is very tempting to use other kinds of functions and write the expressions down like this. Maybe some people would use a decay integration and use functions that are not complete and then start writing down expressions like that. Those are completely wrong. Okay, we'll talk about the completeness axiom after the coffee break. Okay, why only when we do the decay row integration can we write down the solutions like this, not otherwise. Okay, let's take a 5 minutes coffee break.